In the second video for SLO9, we'll be looking at how we can use enolates to functionalize the alpha position of carbonyls. So to get started, let's look at an example with a simple ketone. And we'll choose an example that has only one alpha hydrogen that we can remove, or at least one kind. So we'll look at acetophenone, which is a structure we worked on in the last video when we talked about enolate formation. And one of the reactions that we might want to be able to accomplish is actually to extend the carbon chain from here. Especially what we're interested in doing is making carbon-carbon bonds. These are ubiquitous in organic molecules. You probably take them for granted. Like most of the structures that you're looking at already have all their carbon-carbon bonds. And what you've been learning throughout most of this semester and last semester was how to actually alter functional groups that contain heteroatoms, like for instance alcohols or halides, things like that. We just started thinking about carbon-carbon bond forming reactions in SLO6 when we looked at Grignard reactions and organolithium species. But we can do this in a different way because we know that the alpha position here, which I'm going to label, could become nucleophilic in the presence of a base. And that means that if I wanted to make a carbon-carbon bond, I would need to choose some kind of electrophilic carbon as my reacting partner. And I know how to do that. I could use things like alkyl halides. So one option I could use here is to do some kind of an irreversible deprotonation. Maybe we could use sodium hydride. And I'll make my enolate in the first step. And then once the enolate has formed in the second step of this reaction, I'll add an electrophile, some kind of an alkyl halide. So to get us started with this conversation, I will choose ethyl iodide, so an iodine attached to a 2-carbon chain. And what will happen is that we will effectively substitute the alpha hydrogen for the electrophilic site of whatever species that we add. So we know that this carbon here, the one with the halogen, is our electrophile, that the alpha position can be our nucleophile, and in this reaction, we'll actually attach those two positions. So the product after both steps would look like this. There's still a ketone, and whoops, oh, I caught it, yes. I'll end up with a product that looks like this. So just to be clear, I'm going to actually label this was my electrophilic carbon in the starting material, and this carbon here was my nucleophile because of the presence of the base. So the bond that I made is this one. Pretty cool. So we call this reaction an enolate alkylation because what we're doing is adding an alkyl group to the nucleophilic part of an enolate. We're not restricted to ethyl groups or iodides, right? So what we can think about here is a sense of mechanism. As this will allow us to make some predictions about what other kinds of reactions might happen. So we'll start out with our ketone and our sodium hydride. I'm going to represent that as H-. So essentially the business end. And so what we're doing is irreversibly deprotonating our alpha hydrogen, and I'm going to show the formation of the major resonance structure of the enolate. I'm going to show this acid-base reaction as irreversible. So there's my enolate. Just to remind you, this is in equilibrium. I'm sorry, not equilibrium, in resonance with the form where there's a nuclear or a lone pair and a negative charge on the alpha carbon. And so this structure can then react with our ethyl iodide. Let me give myself some space to do that. So there's my iodine, my ethyl group, And it turns out that the way that this enolate alkylation works is quite literally through an SN2 reaction. So if we were to push arrows from the major resonance structure of the enolate, we would reform the CO pi bond and use the electrons in this highly electron-rich CC pi bond to engage the electrophilic carbon, and the iodine leaving group is going to leave in the exact same step. So this is a reaction that you know already. It is an SN2. We're just using an enolate as the nucleophile here. So that gives rise to our product. So the new CC bond is this one here. And the other product would be sodium from the sodium hydride and iodide, so sodium iodide would be the other compound. So just to recap, we have two different kind of things happening here. We've got the enolate formation, which we talked about in the previous video, and an SN2 reaction. So really we're just using enolates as nucleophiles in a way that you would predict you could use. So let's look at a couple of other examples of this enolate alkylation. So what we'll do is look at different kinds of electrophiles and different kinds of nucleophiles to get a sense for what works and what doesn't work with respect to these enolate alkylations. So another example. So let's say we used this ketone with a phenyl group at the end. And what we want to do is make this ketone. So we're essentially trading one ketone for another, but we're elongating the chain. So my goal is to make this CC bond. And I would need to think about how I'm going to do that. So I know that I've got an alpha position here, and I've also got an alpha position here. But because of the fact that I need to make this product, I know which alpha position I need to deprotonate. I need to deprotonate this one. And that gives rise to this question about, well, I need a regioselective formation of an enolate. I need to pick which alpha position I want to deprotonate. We know how to do this. So we could think about if we removed a proton from this carbon, I'll make a CC double bond here, or an internal one. And if I removed an H from this carbon, if I deprotonate this alpha carbon, I'll make a double bond here. It sounds to me like the kinetic enolate, or the enolate that's less substituted but easier to form because these protons are less hindered, is going to do what I want. And that means that I'm going to use LDA as a base. So my first step, rather than using sodium hydride, I'll use a different base. Right? I'm choosing LDA because I need to choose the regiochemistry of the enolate that I form. And then the next step, I need to choose an electrophile. And the electrophile I choose will be dependent on what I'm trying to introduce. So it looks to me like I'm attaching a methyl group to my nucleophilic enolate structure, which we'll have after the first step. And that means I'm going to need a methyl electrophile. So we could choose something like methyl iodide, CH3I, and this reaction will work the way we wrote it. Quite well, actually. Let's look at another example. So maybe we wanted to take a cyclic ketone. And here I've got two alpha positions, but they're equivalent to each other. So there's no regioselectivity issue that I'm worried about here. So here you could choose either base. Either LDA or sodium hydride will deprotonate this compound, and they'll give you the same enolate. So whatever you like better. I'm just going to use sodium hydride because, nah. And let's use a different kind of a halogen here, just so I make sure that you can see that. We use an alkyl bromide instead. So let's choose this structure. So we've got a phenyl group attached to a CH2 attached to a bromine. And so again, this reaction works the way you would expect. We would form a new CC bond between the nucleophilic alpha position. Nucleophilic because we're adding a base in the first step. So we'll choose that alpha position. They're the same, I'm just choosing them on the right. And our electrophilic carbon here will attach. So my product will look like that. And just to make sure that we're clear about what's happening, this would be the new bond. Okay, so we'll look at another example. So let's choose a slightly more complex structure. So this ketone, and what I want to do is treat this with LDA, and then we'll choose a secondary alkyl halide. So we'll use isopropyl bromide. And to make sure that you are able to predict regioselectivity in enolate formation, what I'd like for you to do is consider what the structure of the enolate would be when this ketone reacts with LDA. So basically I'm asking you to predict the product of the reaction between this compound and LDA. Don't worry about the alkyl halide yet. So pause your video, which enolate forms? So whenever we're considering enolate regioselectivity and we're using LDA, what we're trying to find is the alpha position that has the most sterically accessible proton, because what we're doing is distinguishing deprotonations on the basis of rate. And that's going to basically be driven by whether LDA, or reindeer attack, with all those isopropyl groups, will actually be able to fit inside the structure wherever it needs to go to remove a proton. So what I'm going to do to help me figure this out is label my two alpha hydrogens. So I've got a type like this, that would be alpha to the carbonyl, and then I'll choose a different color to focus on the other possible position. So this carbon is alpha to a carbonyl and has protons. So I would also consider those. And if I look at these two structures, well, this is a little bit different than a case we've seen before with LDA, because I don't just have a methyl group. I have either an ethyl off the ketone or an isopropyl. But the logic still helps me, right? So I can say of these two kinds of protons, red or green, the green protons are going to be easier to access. The methyl group is a lot smaller than two methyl groups. And so we could predict that LDA will remove these hydrogens. They're easier to access. The deprotonation will be faster at this position. Notably, that's going to give me the enolate that's less stable, right? So we're using this kinetic control concept, using reaction rates to dictate what happens. So if I've decided that after the first step, I'm deprotonating this carbon, then I know that this carbon here will be my nucleophile, right? So I want to try to decide which atom is nucleophilic on either side of my carbonyl by using what I know about enolate regioselectivity first. So now I know my nucleophilic position. If I look at my other compound here, my electrophilic position will be the carbon that has the alkyl bromide, or the bromide attached, and so I would expect to form a bond between this carbon and this carbon. So I'll draw the structure of that product. Lots of methyls everywhere. And this is fairly complex. I'm actually going to make the new CC bond red. So hopefully it'll be a little bit easier to see for you. It turns out that this product doesn't form. We actually get the starting material back, but we also get a different product from this species. So I'll say plus starting ketone plus an alkene. So what happened here? I was trying to do an SN2 reaction, but it looks like what I did instead was an elimination. So I removed a hydrogen from, for instance, this carbon. I went from a CH3 group to a CH2 group, and the bromine is also gone. So this looks like instead of an SN2, I did an E2. And this is a consequence of the fact that enolates are strong bases, like we talked about in the previous video. So generally speaking, as you make these electrophilic centers a little bit more sterically hindered, so even like a secondary alkyl halide, what ends up happening is that the elimination starts being a lot faster than substitution. And this turns out to be for the same reason that we actually saw LDA selectively deprotonating these green hydrogens. This enolate is fairly large. There's a lot of structural complexity going on, and it's a lot easier for this nucleophilic and also basic carbon to engage a proton on the outside of this molecule than shimmy its way to this carbon. And so the elimination rate starts being a lot faster than the substitution rate. So what we can basically say here is that really enolate alkylation only works well for primary alkyl halides. Which is kind of an annoying limitation, but it seems to be one that we really struggle to get around because of this intrinsic difference in rates. So in the next section of this video, we'll look at other kinds of alpha functionalizations involving enolate nucleophiles. So let's look at a case where we generate an enolate from another cyclic ketone. So here we'll use cyclopentanone. And remember that in this case, well, in this structure, these two carbons are both alpha positions, but they're the same. So I'm not worried about Enolate Regioselectivity. I'm just going to use LDA because I felt like it this time. I don't need to choose. I just want you to see that you can use LDA if you want in a situation where there's only one enolate possible. So here, instead of using an alkyl halide, we'll actually treat this compound with an epoxide, which you learned last semester is electrophilic at both of the carbons of this three-membered ring. So we know that this nucleophilic position here will engage either the electrophilic position on the left or on the right. And what we established in the last section of this video is that these enolates are fairly large nucleophiles, and they have a very strong preference to react with electrophilic centers that are less substituted. So it turns out that in this case you'd actually find very, very high selectivity for the nucleophile opening the epoxide at this outside or left side carbon because it's much less sterically hindered. And so that tells me that the product we're going to end up with will be a ketone where I've altered the alpha position. I'm going to functionalize it, and I'm going to make a new carbon-carbon bond where I've attached this nucleophilic carbon after deprotonation to this electrophilic position. So I'll put my labels in just so I make sure I draw the right structure. So there's my N, here's my E, and this CO bond will break from the enolate actually engaging the carbon and the CO bond breaking and the oxygen kind of functioning like a leaving group, but it's still going to be attached to this carbon, like you learned about for epoxide opening last semester. And so I'll have my oxygen still attached. And after these two steps, this oxygen is going to be negatively charged. It started out as neutral with two lone pairs, but when the CO bond broke to make way for the new CC bond, the oxygen takes the new lone pair and becomes negatively charged. So I would end up here to start. And then finally, in this case, we need a water workup because we need to put a proton onto this O-. So at the end of all three of these steps, we would have an alcohol. Okay, so you'll also notice that this workup was absent when we did enolate alkylations in the last section of this video. And that's for a good reason. There's actually no type of species that needs to be protonated at the end of the reaction. So once we actually make that new CC bond, all we're left with is like a leaving group, like a halide anion, and there's no strongly negative or strongly basic charges that we need to worry about. Epoxide opening with enolates is a little bit different, right? We have this oxygen that we have to account for at the end of the reaction. So I also want to show you a reaction involving an ester enolate. So if an ester has an alpha proton, we would expect the same kind of thing that we've been seeing with ketones. So these protons are a little bit less acidic than their ketone and aldehyde compatriots, about 25 for a pKa. And we'll talk about why that is a little bit later on in a different video. But we can treat these ester enolates in the same way, or we can make them in the same way. So we could use sodium hydride or LDA. Both of these reactions are going to lead to essentially irreversible enolate formation. So here I'll use LDA. And we can treat this with whatever we want. So it could be with alkyl halides, for instance. So maybe I could do propyl bromide. That would work just the same way we did with a ketone. So this alpha carbon will become nucleophilic, and we will make a new carbon-carbon bond between the alpha carbon and the carbon where the halide is. All right, so here we need to be careful and count carbons. So this carbon is still attached to the carbonyl, and then I'm going to add 1, 2, 3 carbons after the new carbon-carbon bond. So here's my new CC bond. Make it nice and obvious. And then this is my electrophilic carbon. So to make sure that I haven't made the chain too long or too short, I'm going to number things. So 1, 2, 3, 4. And 1, 2, 3, 4. Looks good. 1 is the nucleophilic site, 2 is the electrophilic site. They end up attached. Some people also like to use letters and numbers, so you could call this like A or alpha. And then you'd have like A, and then 2, 3, 4, 2, 3, 4. That works too. But the idea is that, especially if you're making these long chains, if your electrophile, for instance, has this long chain, be careful about dropping carbons. It's very easy to do, but it is something that you need to pay attention to. Okay, so there's one other wrinkle that I wanted to bring in here. I'm going to make myself a little bit of space. And that has to do with stereochemistry. So let's look at an example where we have a slightly more complex ketone like this. And our alpha carbon is a stereocenter. Right, so this is a chiral structure. Our alpha carbon here we've got this nicely defined stereochemical information. The methyl group is back, the proton is forward. We also note that the other possible alpha position here has no protons, so there's only one enolate that can form. And so when we do this reaction, we'll choose sodium hydride as the base, although the outcome isn't going to be dependent on the base here, since we've only got one enolate we can form. And then let's treat this with something simple. So we'll use ethyl iodide again. Okay, so you might be thinking, okay, well this reaction I know goes through an SN2, so the product will be the inversion form. So I'm going to invert this center. So my methyl group would end up wedged, and I know I'm going to attach the ethyl group, and that will end up dashed. So this would be a totally predictable answer because of the fact that we've invoked SN2. But it turns out if you run this reaction, you get another product. You get that. So what's the relationship between those two structures? They're not diastereomers. They're definitely stereoisomers. I think they're enantiomers. Yeah, these are enantiomers. And it turns out you get 50% of each. So that sounds like we've racemized this stereocenter. But I thought that was SN1 chemistry. I thought that was the only time I racemized things. We have to be careful. When we talk about inversion with SN2 reactions, you're talking about the electrophilic site. We're doing something different here. We're racemizing the nucleophilic site. But I bet we can figure out why. So let's think about what happens when the sodium hydride reacts with our ketone. So I'm going to kind of sketch out what I think is going to happen after the first step. So just the sodium hydride. Okay, so I'm going to draw almost everything the same. And I remove the proton, so you're probably going to draw something like this. All right, so far so good. Methyl group is dashed, so maybe this inverts somehow. Well, let's be careful. Let's draw the resonance structure of this compound. All right, so I have something like this, where I've got an O- instead of a C-. But I know that this carbon here, the alpha position, it's sp2 hybridized, which means it's trigonal planar. And that means that we don't have wedges and dashes anymore. This carbon's flat. So these enolate structures make the nucleophilic center flat, just like a carbocation would be flat, and that means the electrophile can come from the top or the bottom in equal ratios. So our nucleophilic center we've destroyed the stereochemical information in this sp3 or tetrahedral carbon by virtue of deprotonation. So we need to be careful when we use enolates to functionalize chiral molecules, especially ones that have stereochemistry at the position where we're going to form the enolate. We'll destroy that along the way. And then we'll get racemic mixtures of the product that forms because the electrophile can approach from either side of that flat enolate structure. Okay, so that concludes the second video. We've talked about enolate alkylation along with a kind of analogous reaction involving epoxides. In the next video, we'll be looking at a special case of reactions which are enormously important, where we actually use enolates with carbonyl electrophiles.